All right, so let's do this from the perspective of the blue car. So from the perspective of the blue car, what does it observe? Actually, let's do it like this to make our lives a little easier. What does it observe? Yes. Faster than what? Faster than who observes? Correct. It's moving faster than you observe it to move. So let's actually see if we can actually define precisely what that thing that we know is true is. And it's called relative velocity. And so the way you write relative velocity is as follows. V of red relative to blue. And I argue that this thing should be defined as follows. And the question is, does that make sense? Yes or no? Why? So this is from blue's perspective. So from blue's perspective, right, it's moving, let's say, a velocity of 3. And red is moving with a velocity of, actually, let's be a little more clear than this. V red, V blue. I would say the speed of red is twice that of blue. And let's give blue a defined velocity. What would blue's velocity be? Well, in order to answer that question, we have to define what we're going to call positive and what we're going to call negative. So, which direction do you want to call positive in this experiment? Call the right positive. Which way is blue moving? To the left, right? Which, therefore, blue's velocity must be negative. So, I'll say blue's velocity is negative 3. And I said that red's speed is twice that of blue. But which direction is red moving? To the right. So therefore, its velocity should be positive 6. So from our perspective, we see red move at a speed or at a velocity of 6 meters per second, correct? What does blue see? Well, let's test this definition to see if it works. So it would be 6 minus negative 3, which is positive 9. So the first thing is this physically reasonable, yes or no? And the answer is yes. And there's 2 ways in which it's physically reasonable. The first way is that blue observes red going at a faster speed than we observe red. Correct? But the other way it's physically reasonable is that blue observes red going in which direction? Be careful. Which way does blue see red going? To the right. And what did we call to the right? Positive. So it's this definition is physically reasonable in 2 different ways. First, it gives the proper speed, right? And second, it gives the proper direction. Yes?
So what is 9 the velocity of the red?
9 is the velocity of the red from blue's perspective. Everybody follow this. So let's actually change this experiment a bit to see how good this is. And what I'll do is I will now set them up like this. What does blue observe? Yes. Correct. Blue observes red going slower than the speed we observe it. So let's see. Let's see if this definition is correct. So let's see that case. In which case, what do we have? In trial 2, what is blue's velocity? Well, first, which direction is it traveling? To the right. What do we call to the right? Positive. So therefore, in the second case, we have V blue equal positive 3. Which direction is red traveling? To the right, which is also positive. So V red is positive 6. So, using that definition for relative velocity, VR relative to B is equal to VR minus VB, which is 6 minus 3, which is 3. Notice, what does this give us? This gives us correct magnitudes, namely that blue sees red going slower than we see it, and it also gives what else? Correct direction. It's positive. Any questions? So this is relative velocity formula. Or if you have two objects, 1 and 2, V of 1 relative to 2 is equal to V of 1 minus V2. And that's 1 relative to 2. And so with that, we start a video. And this is pretty cool. This video was made in an era when people actually thought videos could be educational. How naive of them. So, let's see. As you can see, my kids watch videos. I have 4-year-old twins. Where are my videos? There we go. Enjoy. Let's see if this works. Where am I? Where is the speaker?
We're used to seeing things. We're used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look You look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's talk further. All right. Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. This represents a frame of reference, just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of it is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me. All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things. This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object such as this ball can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is in the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame. Now I want you to watch the motion of this white spot. You probably see the spot moving in a circle. But this is what its path is actually like in the earth frame of reference. This is your normal frame of reference. You saw the spot moving in the circle because your eye moved along with the car. You put yourself in the frame of reference of the moving car. So you see, it isn't always true that we view motion from the earth frame of reference. When the motion is simpler from the moving frame, you automatically put yourself in that moving frame.
And so we're going to get back to this, because this is first in that video. Well, first, that's a 30-minute video that I'm going to be stripping down into little chunks that we're actually going to be viewing through the first 3 units. And that was like a little 5-minute chunk. And it was actually, there's a lot in there. So notice, first thing I want you to just plant, I just want to plant the seed right now. How were they able to determine the correct frame of reference initially? See if you guys, anyone can actually figure this out. When one person was upside down, yes. So in other words, the only way they were actually able to determine this is that you would perform an experiment, and since gravity induces an acceleration, which we have not defined, it's precisely the fact that it's in an accelerated reference frame, the coin, that allows you to distinguish one frame of reference from the other. Otherwise, they're totally indistinguishable. But we're going to return to that point later. But notice, when you were looking at things moving in a relative velocity, they were completely equivalent. So, along these same lines, the very end of this, it illustrates a very important point, which you're going to see when I go and do some examples, or specifically when I go and do the next example, which is relative velocity is kind of like the first exposure into physics, like the real thinking with physics. And sometimes problem solving gets a lot easier when you go into the frame of reference of one of those moving bodies. So I'm going to go to problem number 6. So does anyone want to read this? And you have to excuse me if you find me taking pauses, it's only due to the heat exhaustion. So, if the pause becomes indefinite, that means I'm probably having a stroke. So, who wants to read it? Anyone? You have to be particularly loud. Who here plays football? No one? All right. Fire away, man.
Jim is driving his car at 30 meters per second along a highway where the speed is 25 meters per second. A highway patrol car observes him pass and quickly reaches the speed of 36 meters per second. At that point, Jim is 300 meters ahead of the patrol car. How far does the patrol car travel to catch Jim?
Okay. So, how are you going to approach this problem? Yes?
Well, I was going to say, is the patrol car, like when he passes it, is it moving?
No. Patrol car is at rest, and he has a means of going from 0 to, what is this? 36 meters per second instantaneously. So, how would you approach this problem? I want you guys to talk about it for a second. Maybe even spend a couple minutes on it. And as opposed to actually formally solving it, I want you to sketch out your solution. Meaning, like, think about how you would approach it. And I'll do the same thing. All right. So, anyone have any ideas? So, instead of actually trying to formally solve it, I want to actually walk you guys through the theory of how you approach solving physics problems. So, what's the first thing I should probably do? Okay, this is the first real problem. I'll just be honest with you. This is the first real problem. First thing you should do is, it's the only class besides art where you get credit for, draw a picture. And really, what you're going to be doing is, in drawing this picture, is defining your coordinate system. So let's draw this picture. Now, what do we know? We know at the point where the police officer reaches 36 meters per second, Jim is 300 meters ahead. So what I'm going to do is I'm going to set up a coordinate system that puts the origin where? At the police officer. So here's the origin. And this is where the police officer is, who I'm going to call P. And then where's Jim? Where's Jim? 300 meters away. So here's Jim. And notice V Jim is going this way. And what's his velocity? 32. And what's the velocity of the police officer? 36. Now watch this. Now I'm going to use relative velocity. So what is the police officer's velocity relative to Jim's perspective? Yes. Correct. In other words, V of P relative to J is equal to VP minus VJ, which is 36 minus 32, which is 4. So now, from Jim's perspective, does he move anywhere? Yes or no? Well, who drives here? When you drive, do you move? Do you move? No. You are stationary in your car. In fact, one very easy way to drive very dangerously is to drive by looking in the rearview mirror. That's a very good way to get into a car accident. But what happens when you drive while looking in the rearview mirror? What do you observe? Huh? Who here has done this? Like spend some quality time looking in the rearview mirror while driving? Come on now. Don't lie to me. What you observe is that the cars that are behind you, that are moving at the same speed, look what? They look stationary. That's right. And they look stationary because in your own frame of reference, you're stationary. So you're not going anywhere in your own frame of reference. So what happens? So what happens is that here's Jim. He's looking at the cop in the rearview mirror, and he sees the cop go 4 meters per second. How far does the cop travel? What's the displacement of the police officer? What is it? What's the displacement of the police officer? 300 meters, right? So the displacement of the police officer in that frame of reference is 300 meters. So from this, we can get the time with which it takes for the police officer to catch Jim. How do I find that time? Well, delta T is simply equal to that relative to the displacement between Jim and the police officer divided by the relative velocity. What is it? P relative to J. So this is 300 divided by 4, and you get 75 seconds. Now what? Yes?
Can you multiply that by 36?
And what are you doing when you're doing that?
See the distance.
In what frame of reference? Yes?
Relative to the ground.
Correct. Beautiful. In other words, now you shift into the frame of reference of the Earth. In the Earth's frame of reference, this whole thing took place over 75 seconds. Right? But in the Earth's frame of reference, how far did that cop go? Or how fast did that cop go? 36 meters per second. So, therefore, the distance relative to the Earth, let's say the police car relative to the Earth, is equal to that relative the velocity of the police car times the time. So the velocity of the police car is 36 times the time, which is 75. And what does that equal? 2,700 meters. Is there anyone that actually solved the problem in that fashion? Nice. So that is an example of thinking physics. Notice you could have actually solved this through other means. There are other means to algebraically set things up, solve for some quantity and some ratio, but this is actually thinking the problem through via physics. It's going to take some time to start thinking physics, but by the end of this course, all you will be thinking physics. Yes?
Like an exam, how much work do we have to show, like, to get to the right answer? Like, do we have to show?
You'll see.
Okay.
Depends upon whether it's a free response question or a multiple choice question. I haven't talked to you guys about exams, have I? Oh boy. Yes?
Why did you do that last step? Like, why did you multiply by 36?
Okay. So, in the frame of reference of the Earth, the police car is moving at 36 meters per second. Now, the time it takes for him to actually catch Jim, is 75 seconds. So therefore, relative to the Earth, meaning in our frame of reference, we see that comp travel the product of those two. Meaning, like, we're using, what am I using to solve for the displacement of the police officer in the Earth's frame? I'm just using a rearrangement of the velocity formula, the average velocity formula, where velocity is equal to the displacement over the change in time. So exams, I should probably talk to you guys about exams. Exams are formed from past AP questions, and they're basically split between multiple choice and free response. It's a timed exam. And basically, you're going to be under the gun the entire time that you're taking the exam. Chances are you won't finish. You'll have to guess some. That's just the way it is, because that's the way it is on the AP exam. And part of the year is to train you guys to know how to cut your losses. And I'll tell you right now, if I haven't told you before, I'll tell you right now, no one's getting 100. So the idea of like trying to get 100, you should just ditch it. Your goal is to maximize your score. Maximize it. And maximizing it means sometimes just skipping problems entirely. It's a whole psychology associated with it. And my feeling is it takes about 10 to 15 tests or test-like situations to kind of get you geared mentally to think in that fashion. Any questions on that? All right, so that's relative velocity. So now it's time to go to Paradeck. What do you think of the Paradeck questions? You don't, I mean, if you don't like it, you could just say, I detest it, Mr. Cleo. This is the worst thing I've ever done. This is worse than a 120-degree day. All right. So I just invited the class. Here's your enduring understandings. Along with the enduring understanding, it's enduring the climate. So, this is a slightly different question. This is what's called a ranking task. In this ranking task, you're going to rank the velocities of each of these. And the way you're going to write it, if I'm right, it gives you a prompt for a text. So the way you're going to write it, if two things are equal, you're going to write it like this. A equals B greater than C less than, or greater than C equals D greater than E. Does that make sense? So, I need to time this thing. Ah! God. Excuse me.
How are we supposed to answer on that?
It's written on the board.
But what is like?
Meaning, like, whatever one's greatest is the first one you would put. And if it's greater than, let's say, the next one, you put greater. Character greater. If it's equal to the next one, you just write equal.
Oh, okay.
All right. So, what am I doing? Pear deck. It's asking the magnitude of the velocity. Be careful. Be careful. All right. 15 seconds. Be careful. Notice what graphs these are. 5 seconds. 4, 3, 2. Not many people answered. That's okay. Time. Okay. I'm going to just lock it. Because I think this is a graph that you haven't seen before, right? What is this? What type of graph is this? Velocity versus time. So then how do you find the velocity on a velocity versus time graph? Anyone? What is this? In other words, you just look at what point it is vertically, right? So which one is at the highest point vertically? Looking at this, I would say, yeah, I mean that's tough. I think they should have done a slightly better job, but I would say F looks the highest. So F is the greatest, and what's next? Be careful, because it's asking the magnitude, and the magnitude means absolute value. So, I would argue it is B. And then I think B is just slightly greater than D. And then E. And then C, which is equal to A. Any questions? This is the time to ask. Trust me, if you got a question in your head, that means at least 6 others do. And at least 10 others are lying. Yes?
So you were looking at where the dot was? Or?
Correct. Because this isn't a position versus time graph. This is a velocity versus time graph. So the actual instantaneous velocity is just whatever point it is vertically, whatever its vertical position is on the graph.
So every time we see an instantaneous velocity, that's going to be the case. Like a graph with velocity and time.
Velocity versus time, exactly. Any point is going to give you, the coordinates are going to be time, comma, velocity, yes. Then you would do the, or the, what's the basic word for the derivative? The slope. You would do the slope of the tangent line. Good question. So now, and as you can see, can everyone see that? It's really hard to see on here. Don't worry, I'm going to be publishing this on Haiku right before the exam. All right. The graph of a position. Oh, by the way, none of these are easy from here on. They're all pretty hard. 60 seconds. The graph of a position versus time graph for a car is given below. What can you say about the velocity of the car over time? This is where you need to start thinking. Yes? Oh, that's unfortunate. Really? Refresh. I don't hear you guys. Why do you have to suffer in silence? Ten seconds, guys. Oh, this is too good. All right. 5. Ariana. 3, 2, 1. Lock those responses and show the students' responses. All right. So we've got a majority of people picking D. Is anybody here who's absolutely confident of their answer? What do you think, Powers?
I said not really sure.
Oh, all right. So the answer is.
I'm not sure if this is correct, but
Go ahead.
I thought it was B because it's a graph of position versus time. You're seeing the position there's a greater displacement in the position early on in the graph. Since it's position over time, greater position over less time is greater, so it's slowing down the whole time.
Very good. Very, very good. The answer is B. There we go. The answer is B. So the way you determine this in a very simple way is you look at what happens to the tangent line to the curve. The tangent line to the curve here is very steep. That tangent line to that curve at that point represents the instantaneous velocity. Notice what happens to the steepness as time goes on. Steepness continues to decrease, which means that it's slowing down. Obvious or not obvious? Not obvious, no. All right, this actually is a pretty easy one. In each case shown, someone is running on a flatbed train car as the train moves. In cases C and D, the person is running toward the front of the train. While in cases A and B, the person is running toward the rear of the train. The speeds of the train and each person relative to the ground are given. An observer is standing beside the track watching each train go by. Rank the speed of the runners relative to the observer standing beside the track. Or in other words, rank the speed from your reference frame. All right. 10 seconds. How is you? What'd you say? Rank the speed. It's greatest to least. Greatest to least.
Yeah, if I get this wrong, myself. Ranking the speed, not the velocity. Wait, yeah. But speed is the direction the velocity is the direction of so which one?
Very good. It's the absolute value of the instantaneous velocity. These are all instantaneous velocities. All right. I'm going to call time in about 10 seconds. All right. 5, 4, 3, 2, time. So, anyone? Let's look at this. Clearly, from our reference frame, the one that is clearly going to be the greatest is C. Why? Because he's running on a train, and he's running in the same direction as the train's moving. So from our reference frame, what do we see them move at? 32 to the right. So C is the greatest. Then what? Then now we have to actually do a little bit of math. So looking at these two, they're also moving in the same direction. And so D is giving you 20. So, but B, they're moving in opposite directions. And what do you see? 20 as well. So that tells you D and B are the same. So then you have A. Where is A relative to these three? It's the least. And there you go. So that's what I got. All right. Shown are 5 asteroids in the spaceship, all moving in the same direction away from Earth. The velocities of the asteroids and of the spaceship are given as measured from the Earth. Which asteroids are moving towards the spaceship? I'll give you a minute.
Did they all start moving at the same time?
They're all moving simultaneously. And they're all in the same direction.
Is this relative to the spaceship or to Earth?
This is asking, list the asteroids that are moving toward the spaceship relative to the spaceship. Ah! Blue screen.
It has to have a greater velocity than the spaceship.
20 seconds. Yeah. 10 seconds. Well, I would say, yeah, I would just use letters with commas. All right. 5, 4, 3, 2, Chris, Ariana. All right. Yeah, remember, I can actually see what everyone's responding to in real time. So, no need to hide. All right, so you go into the spaceship's frame of reference. And the first thing you see is E doing what? Yes. Yeah, you see it coming at you. So E is definitely in the picture. What do you see from D? Yeah. Correct. You'll see D moving away from you if you look in the rear view mirror. Similarly, what would you see from C? C would be coming towards you in the rear view mirror. B would be correct. B would be coming towards you, but at a slower rate than C. And then A would look like it's what? Stationary. Very good. All right. We made it to acceleration with 5 minutes left. It's time for me to start talking about it. Ladies and gentlemen, we're at acceleration. And really what this chapter is all about is accelerated motion. And notice I spent how many days now? Is this day 3? This is day 3. And the whole purpose was to get from basically 2.1 to 2.3. Now, by and large, the rest of this, I would say, unit is going to be spent on accelerated motion. As you saw from the reading, what I developed in class was much more expansive than what was contained in the textbook. I mean, does anyone disagree with that notion? I mean, there's a lot more contained here. The textbook is just your starting point for the class. So now, acceleration. So I'll start off by defining average acceleration. An average acceleration looks innocent enough. It's defined as a change in velocity divided by the change in time. So by definition, what type of velocities are we going to be dealing with when you're talking about accelerated motion? You're going to be dealing with average or instantaneous? Instantaneous. It has to be instantaneous. Why? From the very fact that you're saying that there is a change. What does change mean? Change means I can't hear you. It means final minus initial. Right? Well, the very fact that you're saying that something has a final velocity means that it has a velocity defined at a point in time. And the fact that it's a velocity that's defined at a point in time means that is a instantaneous velocity. So let's actually go and develop this out. This is equal to Vf minus Vi over Tf minus Ti. But of course, V is a function of time. So this is actually V of Tf minus V of Ti over Tf minus Ti. And yet again, we go through the same song and dance. You say, Mr. Khalil, this is too formal. Let's set an initial time. What better time to start than 0? Okay. So now you're getting the hang of things. And what better time to call your final time than t? And so you're left with the average velocity, the average acceleration is then equal to v of t minus v of 0 over t minus 0. So, yet again, first type of accelerated motion we're going to analyze is uniform accelerated motion. Uniform accelerated motion means the acceleration is, meaning the same, constant. So what happens, anyhow, what happens, I was scratching the board if you didn't see it. What happens if A is constant? And what am I saying here? When I say what happens if A is constant, what does that mean? That means that what happens if the instantaneous acceleration is constant? So what do I mean by instantaneous acceleration? Well, it would be the acceleration at any instant in time. So what would happen if acceleration is constant? Then the average acceleration equals the acceleration A. In other words, what happens if A is constant and equal to acceleration is constant and equal to A, then we have that A bar equals A. But of course, A bar is equal to V of t minus V of 0 over t, which tells you that V of t is a linear function of time. See you on Monday for lab. Make sure you're done this. Come to me if you have any questions. You will. Yes? What was that? Someone said something about Friday. Lab's on Friday. Hopefully.
Like starting with it?
Yes.
Okay, so I asked yesterday's in the packet, and this one was the wrong one. I had this one.
Okay.
Yeah, I need the lecture questions.
The lecture questions.
Yeah.
Lecture questions. Yes. 1 second. Do you have a bus to catch?
No.
Okay. Give me a second. Sure. Who just came up to me? Oh, there you go. Sorry. Yes.
Because I didn't take, I'm in pre-help now. and
That's okay.
I've been over it.
Which part?
Just tangent, like what is the purpose of it and what?
That means that if you take, let's say, think about driving along a curve. If you're driving on a curve, right? Say you're going fast. What happens? You sometimes hear something, right? All right, what do you hear?
The wind.
It's not the wind. That's actually the wheels. You hear? Eee! Right? So now what would happen if you lost control? Where would you go on this curve?
Down.
Would you go down if you lost control of the car?
Where you start with
You would go like that.
oh.
In other words, here's a curve. You would go off on a tangent.
Okay.
A tangent is a line that is perpendicular to a point. Like that.
Okay.
So when I say that the instantaneous velocity is a line tangent to a position time graph at a point, that means that at that point, this thing has a velocity equal to the slope of that line. And this should make sense. Why? Because slope is a measure of what? Rise over run. What type of units are in the rise?
For position.
Yeah, what type of units are position in? If I were to ask you, what are the units of position?
In the X?
Yeah, what are the units for position?
Integers? I don't know what you're trying to ask.
Anyone? Meters.
Oh, okay.
Right? What are the units of t?
Seconds.
Seconds. So rise would be meters. The run would be second. Meters per second is a measure of.
Whenever you ask for instantaneous velocity, it's just rise over run.
Well, it is the tangent line. It is the tangent line of a position time graph. But on a velocity time graph, let's suppose you have some object
Forgot my question.
that's. You sure?
I forgot my question.
Do you have a bus to go to catch?
No, but my friend's driving me, and I'd otherwise have to walk 1.9 miles in the heat.
Okay, you don't want to do that.
Sorry.
On a velocity time graph, right? Your instantaneous velocity is just going to be any point on this line.
Okay.
Meaning like it's here, it's just some measure here.
So that's velocity time, and that's
Correct.
position time.
Correct. And as time goes on, you're going to learn how to interpret this from this,
Okay.
this from this, and both of these from this.
Can I just take a picture of this because it'll just help me like visualize it?
Sure. It's kind of crazy though.
No, I know, but like I'll be able to like remember what was said. Okay.
Cool.
Thank you so much.
Yes.
So my the haiku thing is going to be done only by typing.
Okay.
So is there any possible way you could catch up without it?
Email. What's the situation with email?
That hasn't worked out yet.
Okay.
Everything's going to be fixed up out there.
I mean, it's not a big deal. So far, nothing major has happened
Okay.
in the sense of assessments. But it's almost like you're kind of missing out on like components of the course. Because I mean, how important do you think haiku is for this class?
Probably very important. I just learned that.
Oh, wait. All right. Let me actually stop this because it just keeps on running.
Is it not important?